In this lecture, we talk about using derivatives to obtain information regarding the shapes of graphs of functions. We ask, what does f prime say about f? Because f prime of x represents the slope of the graph at x, it tells us the direction in which the curve proceeds at each point. If the first derivative is positive, the graph rises. If it is negative, the graph falls. Therefore, first derivative provides information about increasing, decreasing behavior of functions. What does f double prime say about f? We will see that the second derivative provides information about concavity of the function, which refers to the way its graph bends. We are often interested in whether a function is increasing or decreasing. We say that f of x is increasing on interval ab if f of x1 is less than f of x2 whenever x1 is less than x2 in AB. Roughly speaking, function f of x is increasing if its values are getting larger when x is getting larger. F of x is decreasing on interval AB if f of x1 is greater than f of x2 whenever x1 is less than x2 in AB. In other words, f of x is decreasing if its values are getting smaller when x is getting larger. Graphically, function f is increasing if its graph goes up as we move to the right. Function f is decreasing if its graph goes down when we move to the right. To see how the derivative of f can tell us whether a function is increasing or decreasing, let's look at the tangent lines to the graph of f. On the left, the function is increasing, and all tangent lines to its graph have positive slope. Now consider tangent lines to the graph of a decreasing function on the right. All their slopes are negative. So it appears that when derivative is positive, the function is increasing, and when derivative is negative, the function is decreasing. It can be proven by the mean value theorem that the sign of the derivative determines whether f is increasing or decreasing. If the derivative of f is positive on an interval, then f is increasing on that interval. If the derivative of f is negative on an interval, then f is decreasing on that interval. Let's use this test to determine where f of x equals negative 2/3 x cubed plus 7/2 x squared minus 3x plus 1 is increasing and where it is decreasing. First, we need to find the derivative of f. Using the power rule for differentiation, we obtain that f prime of x equals negative 2x squared plus 7x minus 3. Now we need to find the intervals where f prime is positive and the intervals where f prime is negative. Since the derivative is continuous, it can change sign only at its zeros. We set the expression for the derivative negative 2x squared plus 7x minus 3 to be equal to 0. This is a quadratic equation. We use the quadratic formula to find its roots. x1 and 2 equal negative 7 plus minus square root of 49 minus 24 divided by negative 4 equal negative 7 plus minus 5 over negative 4. x1, the smaller root, is 1/2 and x2, the larger root, is 3. These 2 points divide the real line into 3 different intervals, from negative infinity to 1/2, from 1/2 to 3, and from 3 to positive infinity. The sign of f prime of x may change at points 1/2 and 3, but it cannot change on the interval between. Therefore, to determine the sign of f prime on each of these 3 intervals, we need only evaluate f prime at arbitrarily chosen test points inside each interval. For example, on the interval from negative infinity to 1/2, we choose the test point 0. We compute f prime of 0. It is important to make sure that you plug the test point into the formula for the derivative, which is highlighted in blue right now. We obtain f prime of 0 equals negative 2 times 0 squared plus 7 times 0 minus 3 equals negative 3. Because f prime at the test point 0 is negative, f prime is negative on the entire interval from negative infinity to 1/2. We indicate this by drawing a minus in a circle above the interval. Let's pick a point in the next interval, from 1/2 to 3. Since any point between 1/2 and 3 will do, we try to pick a number easiest for computations. Here, an obvious choice is 1. Again, we plug 1 into the formula for the derivative in blue and note the original function. F prime of 1 equals negative 2 times 1 squared plus 7 times 1 minus 3 equals 2. Since f prime at the test point is positive, f prime is positive on the entire interval from 1/2 to 3. We draw a circled plus sign above the interval. The last test point has to be greater than 3. Let's pick 10, since 10 is easy to multiply by. F prime of 10 equals negative 2 times 10 squared plus 7 times 10 minus 3, which is negative 200 plus 70 minus 3 equals negative 133. Since f prime is negative at the test point, f prime is negative on the entire interval from 3 to infinity. We draw a minus above the interval. By the increasing-decreasing test, function f is decreasing when its derivative is negative and increasing when its derivative is positive. We indicate this by arrows pointing down on the intervals marked with minus and arrows pointing up on the intervals marked with plus. In conclusion, f of x is increasing on the interval from 1/2 to 3, and f of x is decreasing on the intervals from negative infinity to 1/2 and from 3 to infinity. To illustrate, we will sketch the graph of this function using the information about its increasing-decreasing behavior. So let's graph f of x equals negative 2/3 x cubed plus 7/2 x squared minus 3x plus 1. We have the following sign diagram. F of x is decreasing on the interval negative infinity 1/2. This means that the graph falls on this interval. We compute the value of the function at point 1/2. We get that f of 1/2 equals 7/24. Therefore, the graph of f goes down to the point 1/2 7/24. The function is increasing on the next interval from 1/2 to 3. This means that the graph rises on this interval. We compute that f of 3 equals 5.5. we draw a curve up to the point 3, 5.5. f of x is decreasing from x equals 3 on. Therefore, the graph goes down from here. In this example, the derivative is continuous, and points 1/2 and 3 are zeros of the derivative. So, by Fermat's theorem, these are the only points where f can have a local extremum. Now we can tell whether it is a local maximum, local minimum, or neither. f of x is decreasing before 1/2 and increasing after. The lowest point on the graph within a small neighborhood is at x equals 1/2. Therefore, f of x has local minimum at x equals 1/2. Similarly, since f of x is increasing before 3 and decreasing after 3, the highest, locally, point on the graph is at x equals 3. Therefore, f has local maximum at x equals 3. Such observations are the basis of the first derivative test for extrema. Suppose that c is a critical number of a continuous function f. If the derivative changes sign from positive to negative at c, then the function has a local maximum at c. If the derivative changes sign from negative to positive at c, then the function has a local minimum at c. If the derivative does not change sign at c, then the function has no local maximum or minimum at c. Let's use this test to find local minimum and maximum values of the function f of x equals x cubed minus 5x squared plus 3x minus 1. First, we need to find the critical numbers of f. The derivative f prime of x equals 3x squared minus 10x plus 3. Critical numbers are the values of x where the derivative either does not exist or it is 0. Since f prime is defined everywhere, to find critical numbers, we set the expression for the derivative 3x squared minus 10x plus 3 to be equal to 0. The roots of this quadratic equation are given by the quadratic formula. x1 and 2 equal 10 plus minus square root of 100 minus 36 divided by 6. Since 100 minus 36 is 64 and square root of 64 is 8, we get 10 plus minus 8 divided by 6. The smaller root x1 equals 1/3, the larger root x2 equals 3. Now we need to investigate whether the derivative changes sign at these points. We position the critical points on the number line. To determine the sign of the derivative between the critical numbers, we use test points. The first test point can be any number less than 1/3, and we pick 0. We compute the value of the derivative at 0. Make sure to plug 0 into the formula for the derivative, highlighted in blue right now. F prime of 0 equals 3 times 0 squared minus 10 times 0 plus 3 equals 3. Since this value is positive, f prime is positive on the interval from -infinity to 1/3. Indicate this by putting a circled plus sign above the interval. The next test point can be any number between 1/3 and 3. We pick 1. We compute the derivative at 1. F prime of 1 equals 3 times 1 squared minus 10 times 1 plus 3 equals -4. Since this value is negative, f prime is negative on the entire interval from 1/3 to 3. We put a circled minus sign above this interval. The last test point can be any number greater than 3, and we pick 10. F prime at 10 equals 3 times 10 squared minus 10 times 10 plus 3, which is 300 minus 100 plus 3 equals 203. Since this value is positive, f prime is positive on the entire interval from 3 to infinity. We put a circled plus sign above this interval. We see that at x equals 1/3, the derivative changes sign from positive to negative. Therefore, the function has a local maximum. At x equals 3, the derivative changes sign from negative to positive. Therefore, the function has a local minimum. Before making conclusions about local extrema, it is helpful to indicate increase-decrease behavior of the function with arrows. Then visually, it is clear that local maximum is at x equals 1/3 and local minimum is at x equals 3. We compute the values of f at x equals 1/3 and x equals 3 and conclude that local minimum is at 3, -10, and local maximum is at 1/3 negative 14/27. Now we turn our attention to the second derivative and concavity of the functions. Suppose we know that f is increasing on interval AB. We can draw its graph in two different ways. In both cases, the function is increasing, but the graphs look different because they bend in different directions. The graph on the left bends upward. The graph on the right bends downward. Informally, a function is called concave up if its graph bends upward, and concave down if it bends downward. To analyze concavity, let's examine how it is related to tangent lines and derivatives. We draw tangents to these curves at several different points. On the left, we see that the curve lies above all of its tangents. The curve on the right lies below all of its tangents. This leads us to the following definition of concavity. If the graph of f lies above all of its tangents on an interval AB, then f is concave up. If the graph of f lies below all of its tangents on AB, then f is concave down. Let's practice to visually identify intervals of concavity. Here's a graph of function f of x on the interval negative 5, 12. Can you tell where this function is concave up and where it is concave down? The graph bends upwards on the intervals negative 5, 1 and 7, 12. The graph bends downwards on the interval 1, 7. Therefore, the function is concave up on negative 5, 1, concave down on 1, 7, and concave up again on 7, 12. Of special interest are the points where the concavity of the graph changes. A point P on a curve y equals f of x is called an inflection point if f is continuous there and the curve changes from concave up to concave down or from concave down to concave up. On this graph, the inflection points have coordinates 1, 3 and 7, 1.5. How does the second derivative help determine the intervals of concavity? Let's come back to our initial two examples and re-examine the tangent lines. Observe on the left that when the function is concave up, tangent lines become steeper and steeper as we move to the right. This means that the slopes of the tangent lines are increasing. This means that f prime is increasing, and therefore its derivative, f double prime, is positive. Similarly, the slopes of the tangent lines to the concave down function on the right are decreasing. This means that f prime is decreasing and its derivative, f double prime, is negative. This leads us to the second derivative test for concavity. If the second derivative is positive on an interval AB, then the function is concave up on that interval. If the second derivative is negative on an interval AB, then the function is concave down on AB. Now we use this test to find the intervals of concavity and the inflection points for the function f of x equals x squared minus 1 cubed. We use the chain rule to find the first derivative. F prime of x equals 3 times x squared minus 1 squared times the derivative of the inside function, 2x. We simplify this as 6x times x squared minus 1 squared. To find the second derivative, we need to use the product rule and then the chain rule. We get 6 times x squared minus 1 squared plus 6x times the derivative of x squared minus 1 squared, which is 2 times x squared minus 1 times 2x. We can factor out 6 times x squared minus 1 to get 6 times x squared minus 1 times x squared minus 1 plus 2x times 2x, which is equal to 6 times x squared minus 1 times 5x squared minus 1. The second derivative is continuous, and therefore it can change sign only at zeros. 6x squared minus 1 times 5x squared minus 1 equals 0 when either x squared minus 1 equals 0 or 5x squared minus 1 equals 0. The roots of the first equation are plus minus 1. The roots of the second equation are plus minus 1 divided by square root of 5. These 4 points divide the x-axis into 5 intervals. We determine the sign of the second derivative on each interval by computing test values within each interval. First, we need to select test points. Here we pick -2, -1/2, 0, 1/2, and 2. Now we compute the values of the second derivative at these points. We substitute the first test number, -2, into the formula for the second derivative, which is highlighted in blue right now. F double prime of -2 equals 6 times -2 squared minus 1 times 5 -2 squared minus 1 equals 6 times 3 times 19. Since this value is positive, f double prime is positive on the interval from -infinity to -1. We indicate this by writing a plus above the interval. The next test point is -1/2. We substitute -1/2 into the formula for the second derivative. F double prime of -1/2 equals 6 times -1/2 squared minus 1 times 5 -1/2 squared minus 1 equals 6 times -3/4 times 1/4. Since this value is negative, f double prime is negative on the interval from -1 to -1 over square root of 5. We indicate this by writing a minus sign above this interval. The next test point is 0. We compute the second derivative at 0. F double prime at 0 equals 6 times -1 times -1, which is positive. Therefore, f double prime is positive on the interval from -1 over square root of 5 to 1 over square root of 5. We write a plus sign above this interval. The next test point is 1/2. We notice that the formula for the second derivative, highlighted in blue, includes only x squared, so it is an even function, and f double prime of 1/2 equals f double prime of -1/2, which we have computed earlier. It equals 6 times -3/4 times 1/4. This value is negative. Therefore, the second derivative is negative on the interval from 1 over square root of 5 to 1. We put a minus sign above the interval. The last test point is 2. As before, f double prime of 2 equals f double prime of -2, which we computed to be 6 times 3 times 19. Since this value is positive, f double prime is positive on the interval from 1 to +infinity. We write a plus sign on top of this interval. According to the concavity test, function is concave up on the intervals where the second derivative is positive, and concave down where the second derivative is negative. We indicate this by drawing lower semicircles over intervals marked with a plus and upper semicircles over intervals marked with a minus. In conclusion, f is concave up from negative infinity to negative 1, from negative 1 over square root of 5 to 1 over square root of 5, and from 1 to infinity. f is concave down on the intervals from negative 1 to negative 1 over square root of 5 and from 1 over square root of 5 to 1. Since the function changes concavity at x equals negative 1, negative 1 over radical 5, 1 over radical 5, and 1, there are 4 inflection points. They have coordinates plus minus 1, 0, and plus minus 1 over square root of 5, 4/5 cube. There is a simple test for critical points based on concavity. Suppose c is a critical number of a function f and the second derivative at c exists. You can see on the picture that if f of x is concave down on the interval containing c, then it has a local maximum at x equals c. If f double prime at c is negative, then f is concave down near c, and therefore f has local maximum at c. Likewise, if f double prime at c is positive, then f is concave up near c. In this case, as you see on the graph, f has local minimum at c. If the second derivative equals 0 at c, the test is inconclusive. In other words, at such a point, there might be a maximum, a minimum, or neither. Let's use the second derivative test to find local extrema for function f of x equals x to the fourth minus 8x squared plus 1. First, we find critical numbers. We compute the first derivative. F prime of x equals 4x cubed minus 16x, which can be factored as 4x times x squared minus 4. Setting it equal to 0, we obtain 3 critical numbers, x equals 0 and x equals plus minus 2. To use the first derivative test, as we did before, we would draw a number line and analyze the sign of the first derivative at the test points. Instead, we use the second derivative test. We compute the second derivative f double prime equals 12x squared minus 16. We substitute critical numbers into the formula for the second derivative. The first critical number is x equals 0. F double prime at 0 equals 12 times 0 squared minus 16 equals negative 16, which is less than 0. Therefore, according to the second derivative test, f has a local maximum at x equals 0. The other two critical numbers are negative and positive 2. F double prime at negative 2 equals 12 times negative 2 squared minus 16 equals 8, which is positive, and f double prime of 2 also equals 8 and positive. Therefore, f has local minimum at both negative and positive 2. Next, we find where f of x equals x over x squared plus 4 is increasing, decreasing, its local extrema, intervals of concavity, and inflection points. We start with increasing, decreasing behavior. We compute the first derivative using the quotient rule. F prime of x equals the derivative of top, which is 1, times the bottom, x squared plus 4, minus the top, x, times the derivative of the bottom, 2x, divided by the bottom square, x squared plus 4 squared. This simplifies as 4 minus x squared divided by x squared plus 4 squared. Since in the denominator we have x squared plus 4, which is never 0, critical numbers are zeros of the numerator. We set 4 minus x squared equals 0 and obtain that x equals plus or minus 2 are critical numbers. They divide the x-axis into 3 intervals, from negative infinity to negative 2, from negative 2 to 2, and from 2 to infinity. Next, we need to select a test point in each of the intervals. We pick negative 3, 0, and 3. We compute f prime at negative 3. F prime at negative 3 equals 4 minus negative 3 squared divided by negative 3 squared plus 4 squared, which is negative 5 over 13 squared. Since this value is negative, the function is negative on the entire interval from negative infinity to negative 2. We indicate this by writing a circle minus above the interval. The next test point is 0. We compute f prime at 0 equals 4 minus 0 squared divided by 0 squared plus 4 squared equals 1/4. Since this value is positive, the derivative is positive on the entire interval from -2 to 2. To indicate this, we put a plus above the interval. The last test point is 3. We compute f prime of 3 to be 4 minus 3 squared divided by 3 squared plus 4 squared, which is again -5 over 13 squared. This value is negative, and therefore the derivative is negative on the interval from 2 to infinity. According to the first derivative test, f is increasing when f prime is positive and decreasing when f prime is negative. We draw an arrow down over the intervals marked with minus and an arrow up over the intervals marked with a plus. We conclude from the diagram that f of x is decreasing from -infinity to -2 and from 2 to positive infinity, and f of x is increasing from -2 to 2. To find the local extreme values, we use the first derivative test. Since f prime changes sign from negative to positive at -2 and from positive to negative at 2, f has a local minimum at x equals -2 and a local maximum at x equals 2. We compute the values of f at critical points. f of -2 equals -2 divided by -2 squared plus 4 equals -1/4. And similarly, f of 2 equals 1/4. Therefore, f has local minimum at a point -2, -1/4, and a local maximum at a point 2, 1/4. Now we turn our attention to the concavity. Recall that the derivative of f prime of x, equals 4 minus x squared divided by x squared plus 4 squared. We compute the second derivative using the quotient rule. f double prime of x equals the derivative of the top, -2x, times the bottom, x squared plus 4 squared, minus the top, 4 minus x squared, times the derivative of the bottom, 2 times x squared plus 4 times 2x, divided by the bottom squared, x squared plus 4 to the 4th. This can be simplified as 2x times x squared minus 12 divided by x squared plus 4 cubed. Since the denominator is never 0, f double prime can only change sign at the zeros of the numerator. That is at x equals 0 and x equals plus minus square root of 12. We position these 3 points on a number line. Now we need to select a test point on each of the obtained intervals. we pick -10, -1, 1, and 10. We compute the values of the second derivative at the test points. F double prime at -10 equals 2 times -10 times -10 squared minus 12 divided by -10 squared plus 4 cubed equals negative 20 times 88 divided by 104 cubed, which is a negative number. The second derivative at -1 equals 2 times -1 times -1 squared minus 12 divided by -1 squared plus 4 cubed. This equals 22 divided by 5 cubed and is positive. F double prime at 1 equals 2 times 1 times 1 squared minus 12 divided by 1 squared plus 4 cubed equals negative 22 over 5 cubed, a negative value. And finally, F double prime at 10 equals 2 times 10 squared minus 12 over 10 squared plus 4 cubed equals 20 times 88 divided by 104 cubed, which is positive. The sign of the second derivative on each interval is the same as at the corresponding test point. We write a minus above all intervals where the test number produced a negative value, and we write a plus above intervals where the test number produced a positive value. We obtain the sign diagram. According to the concavity test, the function is concave down on intervals marked with minus and concave up on intervals marked with plus. We obtain that f of x is concave down from negative infinity to negative radical 12 and from 0 to radical 12. F of x is concave up from negative radical 12 to 0 and from radical 12 to positive infinity. Since the function changes concavity at x equals negative radical 12, x equals 0, and x equals positive radical 12, there are 3 inflection points. They have coordinates negative square root of 12, negative square root of 12 over 16, 0, 0, and square root of 12, positive square root of 12 over 16. To finish the lecture, I will summarize everything we've learned. The signs of the first 2 derivatives provide the following information. If f prime of x is positive on AB, then f is increasing on AB. If the derivative f prime of x is negative on AB, then the function f is decreasing on AB. If f prime changes sign from positive to negative at x equals c, then point C f of c is a local maximum. If f prime of x changes sign from negative to positive at x equals c, then point C f of c is a local minimum. If the second derivative f double prime is positive on interval AB, then f is concave up on this interval. If the second derivative is negative, then f is concave down. If the second derivative changes sign at x equals c, from positive to negative or from negative to positive, then point C f of c is an inflection point. This is the end of our lecture.